This is section 10.3b, ellipses. So today we're going to talk about eccentricity and elliptical orbits. So remember that in the last problem set we disregarded eccentricity, and I told you I was going to tell you about it later. Well, today we're going to talk about eccentricity and elliptical orbits. So these two diagrams represent orbits as you'd find in the universe. A comet's orbit has a more elliptical shape, a more oval shape, whereas the orbits of planets and moons are more round, less oval. Now, in a second, I'm going to talk about why that's true. For now, let's just look at the elements of these orbits. And you'll see that the elements of these orbits are the same as the elements of ellipses as you studied them in the last section. Ellipses have a center. They have two foci. They have a major axis, half of which is A. And they have a distance from center to focus, which is C. Okay, so that much isn't new. If you look here at this more oval orbit, you can see all of those elements. And if you look down here at this more round orbit, you'll see the same elements. And C is just labeled here as the distance from a center to one focus, but obviously the distance from the center to the other focus is the same. It's still C. Likewise, the other half of the major axis, although it's not labeled here, is obviously A because it's half of the major axis, so it's going to equal the other half, which is A. So here's where eccentricity comes in. It's called eccentricity because it tells us how eccentric an ellipse is. And that's because a circle is just an ellipse whose foci coincide with the center. All right, a circle is an ellipse whose foci coincide with the center. Kind of an analogous way to think of this is, all squares are rectangles, but not all rectangles are squares. Well, all circles are ellipses, but not all ellipses are circles. Now, if that doesn't help you, just forget about it, but I know that it'll help some people. And so a circle is an ellipse where the foci coincide with the center. And so you could say that a circle is perfectly centric. But the more eccentric an ellipse is, the more oval it is. Okay, so if an ellipse is a circle, well, it's perfectly centric. But most ellipses aren't circles. They have a center and two foci. And so the farther those foci are away from the center, the more eccentric the ellipse is. And the eccentricity is given by this ratio, E equals C over A. All right, that's just the definition of eccentricity, and it's the C over A. So the distance from center to focus divided by the distance from center to vertex. That is C over A. And so for the more oval orbit, E is closer to 1. And as I said before, this is how comets orbit about a star. And if you look down at this this less oval ellipse, you can see that the foci are quite close to the center. And so E equals C over A is going to be closer to 0. It's going to be closer to 0 because, you have a small numerator and a fairly big denominator. That makes a small number. And the low eccentricity orbits are proper to planets and moons. Now, in the next slide, we're going to look at a little animation of orbits, and hopefully it'll make it a little more clear. But the basic principle to keep in mind is that with the force of gravity, one mass exerts an attractive force on the other. So that's really how gravity works. It's just the masses that it's the attraction that one mass has for another. Well, what keeps us standing on the ground right now, or sitting? What keeps things, you know, sticking on the Earth instead of flying out into space? It's the force of gravity. It's the fact that the Earth's mass exerts an attractive force on every mass that's on the face of the Earth. Okay, well, in the same way, and you'll probably learn this again in physics, uh, if you haven't taken physics already, but in the same way, when something is going around, all right, so I'm going to use my mouse arrow now, and just follow my mouse arrow as it traces this orbit. I'm just going to go around and around and trace this orbit. Okay, so you follow it. Obviously, it's just a rough approximation. This is just to draw your attention. Use your imagination, and something's going around and around. Well, as something goes around a mass, that mass exerts an attractive force on the moving object, a force which would tend to bring that moving object towards the center, towards the greater mass. And that would be true of a perfectly circular orbit. Okay, with a perfectly circular orbit, which actually doesn't exist in the universe, we can make satellites have a perfectly circular orbit around our planet. But with planets, moons, and comets, they don't have perfectly circular orbits. And let me briefly explain why that's true. You see, if we send up a satellite, we can adjust the velocity of that satellite just right so that it'll stay in a perfectly circular orbit. It'll have enough speed to go around the Earth, and it won't have too little speed, which would make the Earth just suck it back into our atmosphere, and it won't have way too much speed, which would send it totally out of orbit. So why then are orbits elliptical? Well, there are many complicated reasons for this, and there are all kinds of calculus-based derivations, but there is a simpler way to explain it, which is good enough for now. All right, the simple way to explain it is this: there is one velocity, and only one velocity, for which an object can have a perfectly circular orbit, and at that perfectly circular orbit, the velocity, the linear velocity that's keeping something going around in a circle, is just enough to overcome the force of gravity that tends to pull the orbiting object towards the planet or star around which it's orbiting. But most orbits are not perfectly circular. In fact, very few, except for satellites, which are man-made. Very few objects do have circular orbits because what happens is that comets, planets, and moons have an initial velocity that comes all the way millions of years ago from the time that they were formed and were spun into existence. And that velocity is more than it takes to keep them in a circular orbit. And at the same time, it's less than would be required to take them out of orbit. And that's why we have orbits that are elliptical. Some are very elliptical if the orbiting object is traveling very fast, and some are less elliptical and more round if the orbiting object's velocity is not much more than is required to keep it in a perfectly circular orbit. This is a little animation to illustrate the points that I was talking about before about how if an orbiting object, an orbiting planet, has too great a velocity, it'll go out of orbit. And if it has not enough velocity, it will simply crash into the sun because the gravitational force is too much. So to show you an example of that, let's say we have a planet here, as you can see with that little blue circle. is just a random planet. And I'm going to give it a certain velocity. A big arrow means more velocity, and a small arrow means less velocity. Let's see what happens if I have a small arrow here. Notice that the sun just attracts it and the planet blows up. Alright, let's try another example. Let's say I have a planet that's quite close to the sun and I give it a significant velocity. See what happens. It has enough velocity to avoid being sucked into the sun. And so what happens is the force of gravity of the sun is keeping this planet in orbit. And yet the initial velocity of the planet is enough to counteract, so to speak, that gravitational force, and so it doesn't get sucked into the sun. This is how orbital velocity works. And notice, I'll give you another example here. Notice that as the planet goes around the sun, as it gets closer to the sun, it has a greater velocity. That's because the gravitational force is accelerating it. And as it gets farther from the sun, it has less velocity. And that's because the gravitational force is weaker the farther something is away from the force that it's being exerted upon. So let's say that a planet is 10,000 miles away from the sun. Well, the sun will exercise less force on it than if the planet were 20,000 miles away from the sun. Okay, so for this particular planet now, its distance from the sun is 104 times 10 to the 6 kilometers. We're going to give it a speed of 31 kilometers, and that's a year of 540 days. Okay, let's let it go, see what happens. Alright, so it's in orbit. Notice how it goes slower when it's farther from the sun and faster when it's closer to the sun. This is how all planets and moons move, and comets for that matter. Also notice that the sun is at the center. The sun is at one of the foci, and if you look at the center where my mouse arrow is pointing right now, that would be the center of this elliptical orbit. It's close to circular, this orbit, but it's still a little bit elliptical. The center of the sun is at one focus, and there's nothing at the other focus. Okay, so where my mouse arrow now is the center, where my mouse arrow is now is one focus, and where it is now is the other focus. And so these elliptical orbits always have the gravitational force at one of the foci, but not in the center. And that's precisely because planets have all kinds of different velocities from when they're formed, and it's very unlikely that a planet is going to have the exact velocity it needs for a perfectly circular orbit. Usually what happens is it has slightly more velocity than it needs to stay in a circular orbit, and therefore its orbit will be elliptical. Now let's see what happens if I have a planet that has a very high velocity. Let's see what happens when I let that go. Well, as you can see, what happened is the sun did exercise a force on it and curve the path, but because the planet's velocity was so great, it will not be in orbit. And so this would be an example of an object that will not orbit the sun because its velocity was so great. Now, comets, what comets do is they have pretty large velocity, but they pass fairly close to the sun, and so they actually do stay in orbit even though it's a very large orbit that goes off this screen. So Halley's Comet, for example, has a very large orbit. That's why it comes to Earth or comes within sight of the Earth so seldom. Okay, so that's just an explanation of why orbits are elliptical and what the factors are. Okay, so the factors are the distance the planet is from the sun, so this would be very close, this is very far. Another factor is the velocity that the planet has. Other two factors are the mass of the star and the mass of the planet. The greater the mass is, the more gravitational force, and therefore the more velocity the planet needs to overcome that gravitational force. So that's just a little interesting demo. We'll put one more planet in orbit because it's kind of fun. Okay, so this would be a planet that's orbiting quite close to the Sun. Has an elliptical orbit. The Sun's at one of the foci. Nothing in the center. Nothing at the other focus. And once again, notice how the planet speeds up quite a bit when it gets close to the Sun and slows down quite a bit when it's far. Let's look at a specific example of an orbit. So this is the lunar orbit, the moon orbiting around the Earth. And just as in the case of the Earth orbiting around the Sun, the way that planets orbit around stars, moons also orbit around planets in an elliptical way with the gravitational center, the gravitational body that's keeping it in orbit, with that object at a focus. Okay, so we see that here. We see the moon orbiting around the Earth, and I'm tracing out the elliptical orbit right now, just roughly tracing it out with the mouse arrow. And so this moon, of course, has a certain velocity. If it had too little velocity, it would just be attracted back to the Earth. If it had too much, it would go out of orbit. But it has just a little more than the right amount for an orbit, for a circular orbit, and that's why it's a slightly elliptical orbit. And the Earth is at one of the foci. So we see here the Earth is at one of the foci. I have a center for this elliptical orbit, but here's the thing that is surprising at first. There is nothing at the center, just as there's nothing at the other focus. And if you look at the way I've labeled things here, C represents the distance from center to focus as usual, and C is equal on both sides, from center to left focus just as from center to right focus. Now it might look like C is smaller on the left and on the right, but that's not true, because this C connects the center to the center of the Earth, and the C also connects the center to the other focus. Well, the distance from the center to the center of the Earth is exactly the same. It's just that because the Earth has a certain diameter, it appears the distance is different, but it's not. It's just measured from center to the center of the Earth. A is, just as you'd expect, half of the major axis. And the major axis, which we know by observation, is 768,800 kilometers. The minor axis, which would be the height of this elliptical orbit, little m, is 767,640 kilometers. Now you can see just by looking at the numbers that the difference between big M and little m isn't that much, and that's why this isn't a very elliptical orbit, but it is slightly elliptical. And therefore, going now to the left of the screen, if E eccentricity is C over A, well, E is closer to 0 and therefore it's more round. Alright, so this is an example of eccentricity, and this would be low eccentricity, which means it approaches a circular orbit. So it's a low eccentricity. Highly eccentric orbits are very oval. By the way, you probably heard the term eccentric in describing people as well. Well, a very eccentric person is someone who's quite off-center. So, the etymology is similar. An eccentric person is off-center. It doesn't mean they're oval-shaped. It just means that they're off-center. All right, so let's continue with this example. These are all the elements, and what you're asked is to find the apogee, perigee, and eccentricity of this orbit. All right, I know that eccentricity is a term already familiar to you, but apogee and perigee are not. So if you follow the mouse arrow, right now I'm tracing a distance from the center of the Earth to the orbit of the moon, from the center of the Earth to the orbit of the moon. Notice again that at the center of the orbit, this point here that I'm circling right now, there is nothing, just as there's nothing at the other focus. The moon, rather, orbits around the Earth, which is at one of the foci of this elliptical orbit. Okay, so tracing out that distance from the middle of the Earth, the center of the Earth,
to the orbit of the moon, you'll notice that at this point, when the moon is at this point, at the far right of this elliptical orbit, at that moment the moon is the farthest it ever is from the Earth. So that's called the apogee. In an orbit, the farthest that an orbiting body is from the mass of gravity around which it orbits, that's called the apogee. And then now tracing out this other distance from the center of the Earth again to the orbit, but this time to the left side of the orbit, that, as you can see, is a much shorter distance. And so that's called the perigee. So in an elliptical orbit, the perigee is the shortest distance between the orbiting object and the body of mass around which it orbits. In this example, you need to find the apogee, the perigee, and the eccentricity of this orbit. So on this diagram, we have really all the elements. C and A and F are labeled. Of course, the Earth is at the other F, the other focus. We've got our major axis and our minor axis, and therefore all the information here is present for you to solve this problem. And you just need to remember that the apogee is the farthest distance the moon ever gets from the Earth, so that would be right here. And right here is where I'm circling around with the arrow. Okay, so that's when the moon's there, it's at its apogee. Now follow the mouse arrow all the way to the left. When the moon is here, the part I'm pointing the arrow at now, that's the perigee. Okay, so pause the video, do this on your own, and then resume when you have an answer. Alright, so going from our diagram, the major axis is given to us, and we know that the major axis, or big M, is the same as 2A, so 768,800. And then also we know that the minor axis is 767,640, so and that equals 2B. So from that we can solve for A and B. We also know, since this is an ellipse, that C squared equals A squared minus B squared. And when you just fill in 384,400 for A and 383,820 for B, you can solve for C, and you get 21,108.47. Therefore, the apogee is A plus C, and that's 384,400 plus 21,108.47, and the apogee then is 405,508.47 kilometers. The perigee is A minus C, and that's 363,291.53 kilometers. I'm going to quickly go back to the last screen just to show you, in case you haven't figured it out already, why it's A plus C and A minus C. Okay, so look at this A here. A is half the major axis, and so I can see that the perigee is going to be right along this line here, this horizontal line, if I am drawing the elliptical orbit. But in the perigee, we're asked for the distance from the orbit to the center of the Earth, not the distance from the orbit to the center of the elliptical orbit. All right, so it's just the center of the Earth, and since that distance is C, then A minus C is the perigee. And likewise, A plus C would be the apogee. Okay, because this distance from the center to the orbit on the right, that's also A, and A plus this C here is the apogee. Okay, so calculating the apogee and perigee, we have 405,508.47 for the apogee, perigee 363,291.53 kilometers, and the eccentricity is simply C over A, and that is 0.0549. So we can see this eccentricity is fairly close to zero, and therefore it's not a very oval orbit. It's quite round. So you would say that it's not a very eccentric orbit. And this is the actual eccentricity of the orbit that the moon makes around the Earth. Here's the classwork, page 750. Please write these numbers down, and we'll see you in class.